Hello friends, welcome to the Boolean Brain in continuation to LeetCode Daily Challenge series where we are solving the daily LeetCode challenge right from intuition to implementation. So far we have covered 28 challenges for the month of January. We are on day 29. Let us take a look at today's problem. The title says minimum cost to convert string 1. So we are given two zero index strings, source and target, both of length n and consisting of lowercase English characters. So it's mentioned that lowercase English characters. You are also given two zero indexed character arrays, original and changed, and an integer array cost, where cost of I represents the cost of changing the character original of I to the character changed of I. Okay. So you start with string source. In one operation, you can pick a character X from string and change it to character Y at cost of Z. If there exists any index J such that cost of J exactly equals to Z and original of J exactly equals to X and changed of J equals to Y. Okay, so we have to return minimum cost to convert the string source to string target using any number of operations. Okay, so total number of operations can be any. And if it is impossible to convert the string source to target, then return -1. Okay, so note that there may exist index ij such that original of j exactly equals to original of I and changed of j is equal to changed of I. Okay, cool. So let us try to understand the problem statement with this example. Okay, so we have given this target, source and target, and we let me write this. Okay, cool. So our goal is to convert each of the character from source to exact same as the character in target. Okay. And in order to do this conversion, we have given these three rules. What does this mean? For let's say we want we want to convert A to A. It is already present, so we are good. Now we want to convert B to C, right? So in order to contain B to C, using this we can convert B to C when in the original, the B in the original and C in the change at a cost of 5. Okay, so if I want to convert B to C, I have to bear this cost of 5. So if you can also observe, B can, so there can be multiple ways, right? So for example, I want to convert B to C. Okay, so there might be possible that from B, I can, I'm just taking a hypothetical example. From B, I can first go to, let's say, A and then C. So my ultimate goal is to go to B to C, but the choice can be like this also. First, I will convert B to A and I will convert then A to C. If the then let's say if this cost was 5 and this cost was 1 plus 2, so my total cost becomes 3. So this way, even though it contains multiple hops, the total cost associated with this is less, isn't it? So I can prefer such kind of statements. So looking at this problem statement, until now you might have been clicked that this isn't a simple string problem. It's more of a graph problem. And how did we identify that this is a graph problem? Because we have a source and we have a target and we have a cost associated with each source to destination, right? So this becomes a simple graph problem. Now, as you might aware, there are different and we have to find the shortest path, right? So it's a graph problem, and we have to find the shortest path. Apart from that, um, we can, it is also mentioned that the cost is positive. Okay, so its distance is positive, and we have to find the shortest path. So from so you might have if this is the given condition, if you want to find the shortest path when the distance or the cost associated of each edge is positive, then we can simply apply Dijkstra's algorithm. What other algorithms do we have? We have Floyd-Warshall algorithm. So Dijkstra's is basically a a uh, single node to all node shortest path, and this basically gives all pair shortest path. So we can apply both these algorithms into this. But since we are already into the series, and as you might aware, yesterday's problem statement was also on the Dijkstra. So this seems to be the Dijkstra's week. We'll try to solve this using the Dijkstra's algorithm. At the same time, another reason why Dijkstra's will work efficiently because it is mentioned that it contains lowercase English alphabetical orders. So how many characters are there? 26. Do we have any other character apart from do? No. So the maximum length, the maximum unique characters in the given source can be of 26, isn't it? So what we can do, for each character or for each of the alphabets like A, B, C, D from source to destination A, B, C, D. So we will try to find the shortest path. We will pre-compute and store for each element from yes to all the elements in A to Z, and we'll store the shortest path. And whenever we are computing, we'll simply add that to our answer, isn't it? This is a effective and clean way to solve this problem statement. Now let us take a look at the solution. Okay, yeah. So cool. So we have given the minimum cost with source, target, the original and the change vectors, and the cost vector. Now first we need to basically build a graph, right? So I declare a 2D vector storing the pair. This pair is nothing but I first try, we are given the this original is giving us character, right? I want to represent it in the form of integers. Why integers? Because that would be a little easy to operate on, because ABCD can be easily converted to 0, 1, 2, 3, right? So that's conversion I'm making here. So if I subtract the ASCII of A from the original, I get the integer value. So I get the UV, and since this it's a 2D, I want to push V in U with this cost. So U to V with this cost. This is how our graph is now represented. Once the graph is created, I declare another 2D vector of 2D vector distance of size 26 by 26 and initially assigned infinity. Why? Because this I want to find all possible combinations distance, right? I will pre-compute that all the difference distance from A to A to B, A to C, A to D, all similarly from B to A, B to B, all characters. So that combination I will do. So I will declare a 2D distance vector. Now, since it is mentioned that all are lowercase English, I'm sure that Dijkstra's will be only executed in O of at max of 26, right? Since Dijkstra's is a single pair to all pair um, shortest, it will give distance from a given node to all. At max, I want to compute 626 times, so I declare a computed Boolean vector to store the status. Then I start iterating uh, on the source string. Uh, yeah, I start iterating on the source string, and at each position, I figure out what is my end goal, like source and destination. And since I want to compute for each character, unique character present in yes, I simply first check if the current character is computed or not. If it is not computed, I simply call the Dijkstras to build the distance from this current source. Okay, the distance, the shorter distance from this to all the characters, I call the Dijkstras. We will see the Dijkstras in couple of minutes. For now, assume that this distance is now updated with the shortest distance associated, uh, shortest distance from yes to each of the other characters. And at the same time, I turn the flag to true. Now I check if now if this is computed, if this distance is computed, I can simply check if distance of s of t, distance of source to destination, is infinity. Why I'm checking for infinity? Because I in the initialization I have filled with the infinity. It's a very large value, so I'm storing it. If the value is infinity, it means there is no path exists. So in the problem statement, it is mentioned that if no path exists, we have to return -1. So we will simply return -1. Otherwise, we will declare answer assigned to initially assigned to 0 and update the answer value with distance of s of t. Okay, because that's the shortest distance we had already computed. Cool. Now let us take a look at Dijkstra's function. So this is taking input as source. So this is an individual function. I would request you to get a hang on Dijkstra's. It's a very simple and easy algorithm, but if you have not went through it earlier, this becomes really challenging to understand it. There are only two steps in the Dijkstra's, one like BFS and the priority queue in order to find. So that's the only thing in this. In Dijkstra's, we get a source, we get the input graph and the distance. We are taking this as a reference because we want to store the values in distance. Now declare a priority queue. So this is the way of declaring priority queue in C++. We are declaring the mean heap. Why mean heap? Because at each step we want to find the node with node with minimum value starting from the source. So initially my source to source value is 0, distance is 0. I push the distance 0 for this source and I start iterating on the priority queue until it is empty. So I start this while loop and I keep popping elements from the top. So this will give me in the first place it will give me the this value 0. Now um, and in Dijkstra, the critical stages uh, at each step, we figure out all the adjacent nodes associated to the current node. So this U is our current node, and this D was the distance, the shortest distance till now when from source to U. Okay, so what we will do, since we know the shortest distance till U, we will try to find all the adjacent edges of the U node and try to relax them. How we will relax? We will fetch all the edges from the graph. This V gives me the node and this W gives me the edge cost. So I check if the distance of V, because V is immediate neighbor of U. So if distance of U is greater than the distance of U plus this weight, if this is the existing difference distance of V was greater than the D plus W, it means it's time to update the distance of V. And where is this distance of V being discussed? Distance of V is discussed from this current source. Okay. At that point, we simply update the distance and we again push back the current node into the priority queue. Distance of V and V. Okay. And that's how this loop keeps on continuing until we get all the nodes sorted. And it's a very popular to know the time complexity of Dijkstra's is big O of V uh, E log V. E basically stands for the edges and V stands for the total vertices. So in V E log V, we can find the Dijkstra's algorithm. Okay, that's why. And if you are observing that we are calling Dijkstra's only once for each unique character. So at max, there can be possibility of having 26 unique characters. So at max, we are calling 26 times E log V. So this is also our final time complexity. Okay, and in terms of space, we are using we are building this graph which is 2D and which is of size 26 26. Apart from that, again this similar of size 26 26. What else we are computing? A Boolean linear array. Yeah, so at max it is of 26 square. So which is, since it's constant, so its space seems to be constant, but in terms of time and space, it is E log B. Okay, cool. Let us quickly try to run this. Yeah, let's try to submit and check. Great. So we have successfully submitted this problem statement. I hope the problem statement and the way how we reached in the solution is clear to you. If you have any queries or doubt, please do let me know in the comments. And if you like the video, please give the video thumbs up and see you in the next video.